us, of course. We would love to talk to you about our approaches for this project on localizing the poachers in Kafue National Park. Let's see if this works. Yeah, this will be our agenda. First, we'll give a short introduction. Then we'll talk about the algorithm, and then our web application that we made. And we have a short demo as well for you to show. Our main question is how to locate poachers in Kafue National Park effectively. Our main focus was to make a web application that would show real-time data, with also the option to show historic data. Our data consists of 181 days worth of observations from 30 sensors, which resulted into 33,000 signals we could work with. This is the team. We have 4 data science enthusiasts and 1 information system expert. We're all here, which is good. So our project consists of 5 main parts. First, we focus on localization. Then we used a Poisson distribution to determine the likelihood of certain signals in areas. Then we used consideration of context, like for example parks and camps and way of entries. And we combined all this into a web application. And of course, we had to test this as well. And this is the main pipeline of going from the raw data to an end product. Now, Philippe will talk to you about localization.
Thank you. Test. So, the first part of process of localization was the data analysis of actually seeing what we're dealing with. And the goals were to clean, filter, prepare the data for further steps. Okay, so basically this is the raw data we received. We had timestamp, ID of the sensor, coordinates of the sensor, and RSSI number, which is from 0 to 255 and represents distance linearly from the sensor. So the first thing we did was kind of change around the columns, which resulted in getting actual distances in number of meters, separating longitude and latitude, and getting an actual human readable date time. And we also noticed a pattern or great imbalance in the data. Basically, this x-axis represents number of minutes in an hour, so from 0, 5, 10 until 55, and the y-axis is the number of detected signals in those minutes. So as you can see, in the first 20 minutes, there are significantly more signals than the others. So what was happening there was the 10 sensors that were really close to the highway were, for the first 20 minutes of every hour, reporting many more signals than usual. We thought that was just a data anomaly because it was synthetic data, and we didn't want to deal with that at all. So we basically filtered all signals in those 20 minutes which were close to sensors. And this is the resulting data set, which is much more balanced. Moving on from there, so the next thing we had to do was, okay, so we have now all the data which we want to use. We have the columns that we want. Now we have to do some trigonometry. To accomplish trilateration, we took every single timestamp where some sensors detect some signals, and then we formed squares, triangles, or just pairs, depending on what's left, what can be formed. Challenge here was because, let's say this is an example of a timestamp in which 9 sensors were active at the same time. So how can you know which detected signals can you combine with which to form what objects, and then to actually apply trilateration process. So to do this, we reiterated over the sensors and their distances as detected signals and their distances, and tried to find the best fit for all possible squares, triangles, and pairs, and then took the ones that were the best fit, of course. And so, okay, so after this step, we have the squares. This is like this specific example how it would, the signal that would result from it. So the third step is actual trial iteration, not triangulation, which uses angles. And I see you keep repeating that. We have just the distances, and so this is an example of timestamp with just three sensors which detect something. And if we just used RSSI to get some distance, we get these three circles, which is not really helpful because all three have to intersect to get some point where we can, you know, say this is where the person or the fun is. Even if we used the data the information that we were provided, that every sensor can detect up to 6 kilometers, and applied that formula, it would still result in something like this. So they're not still all not interacting. So what could we do? We realized that in that case we have three numbers representing three distances from three sensors. We cannot use actual meters, so let's use ratios between those three numbers. And turns out there's a really cool algorithm in trigonometry. Basically, you plug in, you have three known points, you have a ratio of distances to a fourth point for all 3 points, and then you kind of get some cool circles, and where they intersect, that's your point where the signal is. So from the previous example, this would be the resulting spot where the person is, where the phone is. Okay, now Josh is gonna, no, actually, Anina is gonna talk about Poisson.
Thank you. So the Poisson distribution was chosen because it was an option of an elaborate method to spot anomalies in this behavior of the signals across the park. So the first step that we did here was to divide the park into 30 zones, and then we calculated the probability distribution for each zone of the park separately and for each hour of the day separately. So this would result in the probability of a signal appearing at a certain zone at a certain time of day. And it also has the benefit that it uses all the historical aggregated data, where the expected value of that time interval is the main parameter. And also it was beneficial at a certain point in our process because it doesn't require labeled data and it doesn't require context. It focuses more on spotting anomalies. And further, this could be interesting as well in the process of if poachers learn certain activities, this can be used as well to see if they're trying different things because it will spot new behavior. Now Josh will continue explaining our more inclusive method of classification. Thank you.
Thanks, Anina. So we looked at a number of methods to try and classify the different points, but we struggled quite a bit because the data wasn't very labeled and we couldn't find any clear patterns. So we tried using contextual locations to try create paths throughout the park, and then try classify the parks instead of the paths instead of classifying single points. To kind of test this method out, we created about 200 data points ourselves, which we labeled and tested this out to test the different hyperparameters, and we got quite high accuracies. I don't think this would represent fully the real life data, but it was more used as a feasibility study to see if our algorithm worked. In this slide, we can kind of see how the algorithm more worked. We'd start with step one, where we'd find certain contextual locations, such as entrances into the park or tourist lodges, where we knew rangers or tourists would be moving around. And then we'd look for signals nearby that were in a certain radius. And then onto our step two, we'd look for certain signals that is near that first signal and within a certain time frame. And once that location was found, we iterated this to try and create a path, which we could then label or classify as a poacher or a non-poacher. To discuss the testing, we have Mia.
Thanks, Josh. So basically our primary goal was to generate an algorithm and data to test it with, and eventually we thought probably it would be also good to generate a web application, not only for Q42 but also for ourselves to be able to put our algorithm through it and to test it. And we started off with a primary persona, and in our case that was the command center, which is located off the park itself. And we started there, and we tried to describe the persona through a series of Q&As with Q42. Then we found out that probably we ourselves are also the input for requirements. So obviously, because we want to put our algorithm through the web application, and upon the generation of the requirement list, we did iteration of the Moscow approach, which was previously also mentioned. And out of that, we did a prioritization on clarity and distinction between risk and non-risk observations, the representation context of Kafue National Park, and filtration based on date, time, and models. So if we move on, we can see that the intent for the functionality based on the requirement prioritization was the live demo view, which is a specific functionality in our web application, but also to be able to go through a sequence of like a time series upon historic data. So the historic view is generated for that. In the historic view, you have the ability to go through the red views or red viewpoints, which are a series of filtrations based on the models which my colleagues presented. You can make a distinction between the various primary components in our model. Of the web application, we have the cams, the triangles, sensors, we have the smaller dots, which are the regular observations, and we have the possible poaching, which is the red ones. And we actualized our design into web application by actually selecting Dash, by first obviously looking at HTML5 and then more abstract frameworks, but we decided on Dash, which is more specific to dashboard and graphing. And we also eventually considered the fact that there might be some challenges with power and location and information communication, so probably they will also want something which is more remote usefully, so tablet. So therefore we also considered a more dynamic view with Bootstrap. So yeah, in consideration and discussion with Q42, we obtained certain patterns which we kind of use for benchmarking. So we have like the red zones for like the Poacher hot zones, way of entries, we have the tourist route, and obviously the highway. After we generated our dashboard and like the web application, we did some testing. So we applied the classical usability testing with 25 test cases to check the ease of use and performance of functionality. Historic evaluation based on the principles of Nielsen, the algorithm benchmarking, which Josh, etc. did, thinking out loud findings, and also the application of like and scale questionnaires to get an abstract for the ease of use. We applied it, and what came out was that the next iteration should be focused on the completely functional part and the visual part. We looked at that and we made our design much more simpler based on that, and we also revamped our entries for functionality, and upon that it was quite good. So basically, we can now run into our demo. So yeah, it was obviously none of us had front-end experience, so it was quite a learning curve for all of us. So yeah. So we start out with our live view, which showcases in a time interval in a day certain approaches. So basically, it shows throughout the day the various observations and the sensor nearest to that observation, so it can be communicated per sensor type. So you can hover over them and see which sensors there are, which kind of observation, and the color indicates the time of day as well, and whether there are specific crucial observations, they become red. And this goes through on, and you can see that this is in the morning between like 4 a.m. and 8 a.m. and it follows the same route. And we can look at it again later on to see certain more additional significant patterns. In the historic view, you can see the various historic sequences of the data, so you can look through the time as well. So in this case, for instance, we can go through, I don't know, the 24, or like the 29th maybe. Yeah, so basically what you can see is you apply the first filtration on the Poisson, so it basically selects based on the probabilities, and you can continue for the context view, which is the second filtration, and you can see starting something quite interesting, because you see almost a pattern. And you can see at the times that it starts here at 7 a.m., so probably if we consider 7, 8, so if it's 7, 8, now you can see the snapshot of the day actually developing. And this continues. It is quite interesting because if you look back at the previous context control we received from Q42, you can actually see the orange pads going through the more dense red zones, and here as well. Like it starts from 7 a.m. and it moves on to this area. So in the same case, it can be considered such as that the pattern goes to the more concentrated location. We also, so based on this, obviously, with the general view, we can also consider frequencies per like the hours in the day, because these are snapshots in the day, and it can be considered for this. Each view can be snapshotted for communication in PNG, SVG, CSV, and also in the data point part. And that's our demo.